Good afternoon and welcome to the TNS Lunch and Learn series. This is brought to you by Tactical Network Solutions, and my name is Heather Eastman, and I'll be presenting today. Usually I have Craig Hefner here with us, but it's just me today. So I hope you find today's talk interesting and possibly useful for some of your daily tasks. Moving on. This particular Lunch and Learn series had 5 different sessions happening every 2 weeks. We're in the 4th session, which is the memory analysis. We have one more coming up, and all these sessions are going over some hardware analysis techniques that are used by reverse engineers, and it's geared towards actual, hardware techniques, the hardware techniques versus the software. There's a lot of things. There's two divisions, if you want to say. There's stuff that you have to do to interact with the hardware. That's the side that we're trying to keep. We're trying to, bring all that information to you here, versus what you do afterwards after you get like the data or the firmware or something like that, and you plop it into like IDA or something. That's a little bit more software side. We're trying to keep it all hardware. So that brings me to my next thing about memory analysis. Memory analysis, this particular talk is about memory analysis from a hardware perspective. We're going to take a look at the chips, possibly take a look at what we're going to find on an embedded system, discuss the types of differences between them, and then possibly show you, or we're going to show you how to extract some data from them and what are the possible obstacles you might come across when you're trying to extract the data from these memory chips. So let's get started. So the types of memory you can come across on an embedded system, they can be put into one of 3 categories: RAM, ROM, or hybrids. So RAM is volatile. It's read access memory. The data that you put into RAM will be retained so long as there's power to the system or power to the chip. Once the power is lost, then the data is lost also. ROM is non-volatile, so once the data is retained even after the power is turned off. It's always going to be there unless you erase it yourself. And the last thing we have is hybrids, where it's a combination of the aspects you see inside of RAM and ROM that are put together into those characteristics are shared inside of a hybrid integrated circuit device, like a little memory chip. So let's take a look at some RAM. This is static RAM. So static RAM is something we're almost everyone should be accustomed to. Static RAM. Static RAM is essentially the same type of memory you're going to find inside of a desktop. So once the system turns on, you start writing to RAM. The data is going to be retained so long as the system is powered off, and as soon as it's powered off, then you lose the data. So these two are 2 different types of RAMs. One smaller, about 256K, and the one on the right, the Cypress one, is about 4.5 megs. This is typically what you're going to find. All these chips are somewhat like rectangular and a little flat, depending on the type of chip it is and who's manufacturing it. It may be big and planar, like this, like the Cypress one. It's very big and squarish looking, but it's very flat. And they usually have these leads coming off of it. So this is static RAM. The other type of RAM we will come across is dynamic RAM. And dynamic RAM is where the data is short-lived. It requires some refreshes to maintain the data over time. So there's going to be a threshold, depending on what type of chip you buy and who you buy it from. There's some characteristics about how often you need to refresh the data in order to maintain it. It usually is on a scale from a few nanoseconds to a few milliseconds. It depends on what you actually need. And each one of these memory chips is based on what you're trying to address, the type of system you want to put it into, and how often you need it to, rewrite your data. So the one on the left is an ISSI, and the one on the right is an ESMT. So those are the 2 types of RAMs you might find on a system. Next, we're going to take a look at some ROM, and we're going to start from the bottom. There is sort of an evolution of where ROM came from. So you may find some masked ROM on some embedded systems. Like today, to this day, I have only seen one, but it's good to know what masked ROM is. And if you're interested in, you know, having masked ROM produced for you, these are the two companies that can, that will still take an order and still, you know, manufacture masked ROM for you. This is Macronix on the left, and on the right is Renesas. And so what masked ROM is where the transistors are arranged in the chip before manufacturing. So they decide, you know, they encode all the data that you want encoded into the memory space, and then they basically manufacture the chip like that. So you're not going to be able to change it after it gets to you. It's going to stay the same. This is something where you have, like, I don't know, maybe a legacy boot code that's never going to change. It's always going to turn on the same way. This is what you would go with. And it's very cheap, because then once you, I think you can get them for like 70 cents a piece or something, but you know, you're going to have thousands of these little chips that are going to all have the same code. So it's really up to you how you're trying to build your device. So one step up from masked ROM is programmable read-only memory, or PROM. And instead of the manufacturer arranging the transistors, the end user does the programming. So we take this chip and we plop it into a programmer, and we basically set the transistors to the way we want. And this is definitely a one-time programming device. So once you program it once, you can't reprogram it again. There's a one-time programming, and it's done by the end user. The left one is a Texas Instrument. The right is AMD. I've seen a couple of Texas Instruments on a few devices, but I have not seen an AMD. So how do they program these devices? Well, here's a PROM programmer, but I could not find this programmer under, I mean, you do Google search, and you say, I want a PROM programmer, you're not going to find one. It's going to come up with some odd results. But if you search for bipolar ROM programmer, then you're going to find this guy. It's the Advent Super Pro 6000. And this one, this supports a variety of chips. I believe Altera is one, Atmel's one. I can't remember the other manufacturers that Advent supports, but if it depends on what type of device not the device, but the memory chip you're trying to program is and who supports it, then you can use that to program it. But this is a PROM programmer. This same programmer can also do EEPROM. So EEPROM is one step up from PROM, in that EEPROM is erasable, whereas PROM was you can only program it once, and then you can't program it again. Now this one's erasable, and this is a little bit more expensive than PROM. And the way it's erasable is using some UV light. Some UV light has to pass through this window on the left chip. There's the ST chip on the left. There's a little window. You apply some UV light to that, and then the transistors move back into the default state, and then you can reprogram it, plop it back into the programmer and reprogram it. The one on the right is it's the same packaging of the one on the left, but it's a one-time programming package because there is no window. So this is a EEPROM, but an EEPROM package with the characteristics of a PROM. So you can only program it once. So what does a UV eraser look like? Advent also sells the same UV cabinet. So they have a bigger cabinet, they have a low volume cabinet, a medium volume cabinet, depending on how many chips you're going to be erasing at the same time. Most often, you might find, I wouldn't even use this, but this is just something we need to cover. But Usually what they did in the past was take these chips, write some code, debug it, put it into their system, debug it, find out what's wrong. If something's wrong, they take it back to the UV eraser, plop it back in for 11 to 13 minutes, plop it out, do a program again, and then, vice versa. This is a whole like circular type process. Program, try, repeat. So that's why you would have a UV eraser, and that's why it was useful to have EEPROM, so that you didn't have a slew of PROM chips just like being tossed away after each iteration. So what's next from there? So you have, the worlds of RAM and ROM, and there's good things on both sides, but what they did was like, well, let's take both of these two things and sort of, the good characteristics of both sides and try to come up with something better and something that's much more useful, faster, and you don't have to use this, like, get rid of this UV eraser type thing. But, so we have RAM, which is read-write. You can read and write it, read and write memory, and it's volatile. Whereas ROM, it's only read-only. You can't write it again, and it's non-volatile. The data is always going to be maintained. So the next version, the next step up from EEPROM was WEPROM. And with WEPROM, it is now we no longer need this UV cabinet. We can now erase the data electrically. And you just basically supply it a high current. And once you apply the high current, then it resets all the transistors for you. And you use the same sort of programmer as you saw as I presented back when we were talking about the PROM. That same type of programmer, the same type of programmer is what you would use to reprogram this WEPROM. So WEPROM is something that we've used for a while. They come in various types. They support various types of protocols. Most often you'll see SPI serial WEPROM, which is the one on the left. And the only drawback for WEPROM is the amount of times that you can rewrite. You can write, erase and write over EEPROM. The ST chip is less than 4 million writes. The Atmel chip is about 1 million write cycles. And then how long the data can be maintained on these two devices. ST says they can retain the data for up to 200 years. And then Atmel says, well, we can do about 100 on this chip. So one thing to take away is that if you were in our previous sessions, we talked about looking up like OS, sorry. We talked about finding data sheets for these devices. And if you notice the difference between this and what you would find on a microprocessor or a Wi-Fi controller, depending on what it is, the marking is very, it's not, I don't want to say cryptic, but it's very shorthand. A lot of times, depending on which manufacturer you're looking at, the markings could be shorthand or truncated, if you want to say. So looking at the Atmel on the right, this is actually a truncated version of the actual model number. So if we go to the next slide, we're going to take a look at the topside markings. And what I really recommend is if you find a memory chip where you're not able to find or correlate a data sheet to, you should definitely put in your search terms the, let's see, Atmel ATML H136 and then space and then put 46D followed by topside markings. And then that will give you, it'll give you a few PDFs, something closer to what you're actually looking for, which is how I found this particular data sheet. However, I had to do some additional digging. I had to go down into like page 11 out of 15 or something. And there was this tiny table here. And if you look, this little tiny like table at the bottom where it says catalog number truncation. the truncation code is 46D, and the actual part number or the catalog number is 1896C46D. So this actual chip on the previous page, which is the Atmel on the right hand side, is actually an AT93C46D. And that is the AT93C46D is actually the value and the name that you're going to find at the very, very top of the data sheet. You're not going to find 46D. You're going to find this other catalog number. And then how you can correlate that back is you go back up in the same page, but just a little bit higher. It's going to show you the 8-lead SOIC package, and it's going to have exactly the arrangement of the letters exactly how it matches up to this very first one where it says the 8-lead SOIC package. So you have to kind of correlate the package type with some lettering, and then you get further down in the data sheet, you're going to see this thing called truncation code. This is only true for Atmel, but it's for this particular example, it's for Atmel, but you're also going to find the same sort of shorthand truncation code like numbering scheme in other manufacturers, and we'll see that in a couple of slides down. But moving on, so another step up from WEPROM, we are now into Flash. So Flash is a little different in that you don't have to supply this high value of current. It's easily erasable. For every time you want to write a new, write to the Flash, you have to do an erase before you do a write. In these ones, you can do about 100K erase program cycles. It's a little bit more, it's a little bit less than the WEPROM, because what we were looking at in the WEPROM was like 4 million and versus 1 million, and now we're in about the 100K or less than 100K. So the Macronics, I'm sorry, backing up 1 second. When we take a look at the chip on the left, this is actually a Macronics chip, but the logo is different. If you take a look closely, the logo is like this K, backwards K with an H. So Macronics has a manufacturing plant in Hong Kong. So this particular chip is the same as all Macronics internals, but it's manufactured in Hong Kong. So you're gonna find that you're not going to be able to find this data sheet. So the way the way we found it and how we looked it up is we searched Macronics for this 25L3205 DM2C, and we were able to find something similar. And what we came up with was that this particular chip was a 32 megabit serial SPI flash. If we hadn't found that this was the Hong Kong version of Macronics, then we would have been searching forever. You go to these weird websites and it doesn't really, you don't really actually find the actual data sheet. So I highly recommend looking at the Macronics site versus the Hong Kong Macronics site. But another thing to take away about this naming convention they have on these chips for all these memory chips, usually the value that comes after the letter, so 25L and then the letter, and then on the right side with WinBond is 25Q64. The 32 and the 64 both are sort of synonymous with how big that chip is. So you're going to start to see some correlation between that. So the left one is a 32 megabit, and the right one is actually 64 megabit when you take a look at the data sheet. So WinBond is another good example of how the topside markings are truncated. So if we take a look at this and we try to put 25Q64BVFIG into Google, it's not gonna give us anything useful. So if you add like the search term topside markings, you're going to actually get a useful PDF if you do some searching inside that within that PDF, you're going to find way down the bottom another table that's going to correlate between a topside marking and an actual product number. So if you look at the bottom table, this is also 25Q64BVFIG correlates to W25Q64BVSFIG. And if you do some further research, you're going to find that that is actually correct. It's a 16-pin SOIC. So if we go back and we count the number of pins around this package, and we do have 16. The example above is for, I believe it was for STM, ST microelectronics. So STM also abbreviates their markings on their particular chips. All of them are 10-digit. So, or the maximum number is 10-digit, but their 10-digit value goes back to correlates back to a marketing part number, which is for this particular example, 25P32V6P correlates back to M25P32, and it says VMF6P. So that package is so when you put that package or the marketing part number into Google, then you're going to find a valid PDF for that that memory chip. So what is the difference, or what are the differences between double EEPROM or flash? So the good thing about double EEPROM is that you can access their data byte-wise, whereas flash, it's block-wise. You have to read a block at a time. Double EEPROM is seldomly rewritten because you have to essentially pull the chip out, go back, erase it, put it back in. It's not something you want to do on the fly. Whereas flash is in circuit, it can stay in circuit, and you can rewrite it at the same time. Rewrite, erase it, write it, read it, however way you want to maintain your data inside of flash. However, you're not going to be doing that while on the fly or what. Depending on how you're using this flash chip, you probably aren't going to be rewriting it often because it's very slow when you write to these memory chips. But the double EEPROM comes in smaller storage spaces than the flash. So the double EEPROM, you're going to be looking at like a few kilobits to a few, a couple of megabytes, not kilobits, but kilobytes to about a couple of megabytes. Whereas for flash, you have a little bit of a leeway of a larger storage space, and you're going to have, gigabytes to hundreds of gigabytes. So, but flash comes in two different types. You can have a NOR flash or a NAND flash. NOR reads faster. You can do random accesses to NOR. It's usually, NOR is memory mapped in, typically. And you have slower writes and erases when you're working with NOR. And it usually comes in smaller densities. Whereas NAND, you get slower reads, but you get faster writes and erases. And it's you have higher density or higher capacity of data storage with a NAND. So back to NOR being memory mapped, and NAND is usually IO mapped. NOR is better suited for code storage since it's memory mapped in, and you can do some execution in place. And then NAND is better suited for like data storage. So when you want to save off your data or something like that. And the reason why you get smaller densities for NOR is because when you manufacture a NOR transistor versus a NAND transistor, a NOR is almost twice as big as a NAND. The NAND is very tiny, so you can get more of these transistors in a tiny space than a NOR. So which is why NAND would be NAND will give you the higher data capacity. And the last type of hybrid we're going to cover today is NVRAM, non-volatile RAM. That's kind of funny, isn't it? When you think about it, RAM usually doesn't maintain data after it's off. Well, the way they came up with NVRAM, non-volatile RAM, is they basically put batteries, lithium batteries, into the chip so that it can, maintain power after the chip or the device is turned off, so the chip maintains power using the battery, using these backup batteries, and the data is maintained. But Cypress many semiconductors, you don't need batteries. You don't see batteries on these things, and this is why the NVRAM is kind of big. It's a big chip you're going to find on a system. But the right hand side, the Cypress one, is actually, this is a new thing. They don't need batteries. This chip does not have batteries. I'm not sure of how they got this technology to work, but if you're interested in it, go over to Cypress Semiconductors and take a look at their new NVRAM. Okay, so we're talking about the companies that make these chips. So what are the most common companies you might find? I've found quite a bit of Micronics, which is the MX stuff. I've seen a couple of Microchip. I've also seen ST, Atmel, Cypress. Usually when you see Cypress, you're not going to see the word Cypress. You're only going to see that little tree on the chip somewhere. Winbond has the whole name on it. ISSI will also have just its the ISSI. Texas Instrument has the TI, or that little Texas with the I inside of it. I think that's all I've really actually seen. The rest of these companies also produce memory, but these are the bigger ones. The bigger ones are the ones I discussed just now. So I'm going to let a few people here take a look at a board, and I will put up a copy of it for you to take a look at home. So what we're going to do is we're going to inspect the board, try to locate the memory components. When you're looking at this board, ask yourself the question, how many memory chips are there? What type is it? You should be able to kind of discern the differences, and possibly if you can see the markings on the chip, you might be able to quickly discern what density the particular chip is. So while we pass these boards around, I will put board number 1 up there for someone to take a look at. There you go. Take a couple of minutes to look at this board and see what you find. Okay, so let's go over the board really quick. Looking at it right off, we can ignore all of the Broadcom chips that are on the board. We're also looking for something that's very flat and rectangle looking. So if you look at the board, there's only 3 chips that look of interest to us right now, or you should be interested in. It's this chip here and these 2 down at the bottom. The rest of the chips are not what we should be looking for, but if we if we dig further down, that is very true. These are the memory components for this board. All of the boards, all of the examples we're going to take a look at have a blue or teal rectangle around the non-volatile memory, and then we have a green rectangle or square around all of our volatile memory. So here we have a I'll read off the product number to you, and then I'll tell you exactly what the size is and what type it is. So we have an MX290LV320CBTC, which is the blue or teal box, and that is actually a 32 megabit flash. And I don't have this is a parallel flash because of its the bigness of it, and the many pins that are around the chip. And then we have down at the bottom actually is our IC42S 16400. So when we're reading these numbers off, usually the number that come after the second lettering is usually an indicator of how big the chip is. So 16400 is actually a 64 megabit SDRAM. It's made by Integrated Circuit Solutions. So that's our board 1. Here's board number 2. Please take a moment to look over this board, and we can discuss it in a second. Okay, so coming back, as we did in the last slide, process of elimination or looking at big flat chips, we can kind of assume that this might be the memory chip. These square ones are not. Something down here looks of interest, but I'm not really sure which one it is. But when you look closely, this has actually an MXIC, and this is a L4 something. I'm almost going to say this is probably not our chip. It might be this one, because I've seen after many times looking at a board that MXIC is a name for Micronics. So when we look this product number up for the non-volatile memory component, we find that it's an MX25L and then 6406 EM2I, and that is actually a 64 megabit serial flash. And then we have the top one, which is a M12L 128 168A, and that is actually a 128 megabit SDRAM. So it's kind of low on the size, the capacity. So if you actually, this same board, I flipped it over, and there's actually another RAM chip underneath. So there's two SDRAM chips. Just one is on the back side. I didn't take a picture of it. Board number 3. Take a look really quick, please, and we'll discuss it pretty fast. I think after a couple of boards, I think you're pretty. You probably should be able to pick these out pretty quick now. Okay, let's take a look. I only see two big, really flat, rectangle-looking chips. So I'm pretty sure you can see that there's this one here, the MX one, and then there's this funky, weird named one here, named IC. This big one is definitely not it. Not a memory component, and neither is this stuff over here on the right. So when we take those numbers and we plug them into Google, do some searching, we actually do find that MX chip is also a Micronics chip. It's actually MX29LV 800 CBTC, and that is an 8 megabit parallel flash. So that's another parallel chip versus a serial. So these parallel chips you're going to get are pretty big. They're almost as big as a RAM chip. So you have to pay attention a bit. And then the second one, our volatile memory, is actually made by Hynix. I think that's how you pronounce it. If not, please don't hold it against me. But this is actually an HY57V641620 ETP, and that is a 64 megabit SDRAM chip. So we're strolling along, going along very well here. Let's look at board number 4. Anybody have any questions so far? No. Okay. Taking a look. Oh, this board has a chip missing. We took it off. We're doing some analysis on it. But it was the only board we had. That was another interesting one. So for those who are tuning in, you're not going to see this very well, but for those in the class, they can obviously see that there's only one memory chip on here, and you can see that too on people tuning in, that this is a memory chip here, the rest of it is not. So when we actually look this up, we are going to find that this is a RAM chip. So we're like, okay, we have RAM. Well, there has to be some non-volatile memory somewhere. So for the people who are in the class, this was a trick board. I can't remember who got it, but the non-volatile memory is on the back side, and we'll see that in a second. But the volatile memory in the front is actually made by Elite Semiconductor Memory Technology. The product number is M14D 512-163-2A. So it's a 512 megabit SD-RAM chip. So when we flip the board over, the non-volatile memory is on the back. Sometimes this will occur, but not all the time. Usually it's on the front side. So this is actually a Micronics chip, and looking at it versus the types of Micronics we've seen, we can sort of, say that this is a serial chip or serial flash chip versus a parallel. It's not big and flat. So the value, or the number you can look up is MX25L 6406 EM2I, and it's a 64 megabit serial flash chip. So what's the importance? Why do we care about memory? And more specifically, why do we care about non-volatile memory? Well, it contains data about the system. What type of data would we typically find when we're looking at non-volatile memory? Well, we possibly could find a kernel or a file system or bootloader, or maybe we might just find a MAC address. There's all these possibilities. There's some stuff, whatever information needs to be stored in order for the system to come up is usually what we're going to find in non-volatile memory. So the type of boot sequences you might come across when a system comes up, or a system is coming up from a power on or a reset, is there's two types you're going to come across, either a single stage or a multi-stage. So in a single stage, you're more than likely are going to have some internal boot ROM. Processors and chips without internal boot ROM will possibly be doing the multi-stage one, the multi-stage boot sequence. So for when it has internal boot ROM, it'll just set up everything and it'll just start running. You don't have to copy anything from anywhere. So it's a single stage. And it's usually probably running out of Flash or something, because it's pretty fast, versus like WEPROM or anything like that. What are the common OSs you might come across? Linux is the most popular. Then you have VxWorks. You may come across some Cisco iOS if you're looking at routers, Windows CE if you're looking at some mobile, or you can do other stuff like I can't remember. Android. Android's probably not one. I want the Android, but it's Linux based. Moving on, what type of bootloaders you may come across when you're looking at embedded systems. U-boot is the most popular. A lot of times, a lot of these systems, or the routers we look at, are based on U-boot. Use the U-boot loader. Bearbox is basically a U-boot version 2. It's the workaround solution for the limitations they found in U-boot. And then if you're using the ECOS operating system, which is also should have been listed on the previous slide, but it's not. I mean, I don't have any experience with ECOS, but if you do, you're more than likely going to be using this Redboot, the Redboot bootloader. And there's other bootloaders out there, but these are the most common that you might come across. What type of formats is your firmware going to be in? Depends on what type of system you're looking at and how it's been implemented, and how people are pushing firmware updates and stuff like that, or how they're going to be supporting their product after it's been sent to the end user. You could actually have a system where it has a complete full system, a full-blown system with a full OS and kernel, and it'll have a bootloader and possibly some libs and support libs and the applications. But the applications, if it comes in this full-blown version, the applications are usually running in user mode. The next one's like an integrated solution. Usually you have a proprietary OS, or either that you don't have an OS at all. and the OS comes as a lib, and then you have these applications that are along in this particular archive usually run at kernel level. And then the very last one is like a partial implementation where you only have applications or libs or resources or some sort of support files, and you're just getting updates for the files that you're concerned with. So it may be that if people are doing like one-offs between products, like one product gets one type of feature set, the next one gets another feature set, it may be this partial update where you're sending only updates for certain types of features. Next is how next about the formats is how they're actually put into the memory section. You can find them as like pure archives. It can be this giant tar file or a giant gzip, or it'll be compressed into like a bzip or lzma, or actually it might be an rpm, who knows. Or it can be a pure file system, so you can just take it and mount it if you wanted. And usually some of the file systems that are found in these embedded systems, either YAFs or JFFS2 or extended NFS. Or it could just be a binary format, which usually the more common ones you might find is SREC, IHEX, or ELF. Now, what if you have everything? What is it going to look like? What's the typical layout you may find if you have this full-blown version? Well, there's going to be some sort of firmware header that's going to tell you how you're supposed to like decompress or extract data out of this particular section of memory. There's going to be a firmware header followed by possibly a compressed kernel, and then some padding between the kernel and the compressed file system, followed by some padding at the very end. So how do people normally extract data from these memory chips? Well, there's only two ways. Well, there's two basic methods you can use. First, you can try to extract the data from the memory component itself, or you can try to extract the data over a debug interface, but the system would be up and running. So we'll take a look at how we extract from the component itself. Here is an example. What you normally need is this, when you're doing extraction over SPI, this is a really good cable to have. It's a C232HM. It's based on the multi-protocol synchronous serial engine, the MPSSE. It can handle up to about 30 megabits per second on over JTAG or SPI or I2C. Oops, sorry, wrong way. And you need to download a couple of support applications. You will need the libmpsse library for interfacing with SPI and I2C devices. And you need the library because there is an FTDI chip inside of the USB, the little USB cable. It's actually the FT232H, and this helps you interface with the devices so that you can read over SPI. Binwalk is a tool for analyzing and REing and extracting firmware images. That's just what we use to extract our firmware images. We have Sasquatch. Sasquatch is basically a modified version of Unsquash FS, and all it does is just decompresses and extracts squash file systems. So we took a look at TrendNet, this TrendNet router, the TEW733GR. So how did we get started? Well, we take the cable and we have to figure out what the pinout is for the memory component. So we have to do a little bit of research, take a look at the component, plug it into Google, get a data sheet. Once we get that data sheet, we can figure out what the pinouts are. Once we find the pinouts, and then now we have to take the cables and hook them up correctly. And usually red is always power, and black is going to be ground, so we can instantly attach the two. And I put the table for what the cable, this C232H, the legend is for the color coding for an SPI serial interface. So here is how we did it. Red to VCC, black to ground. Orange is our clock, so we hook it up to the S clock of the chip. Yellow and green are definitely two things you need to make sure you hook up correctly. So yellow is actually an output, which is an output of the cable. So when you're dealing with SPI, you have to make sure that you have them switched so that, like, you know, in like master slave mode type thing. So the output of the cable has to go to the input of the chip, and the output of the chip goes to the input of the cable. So if you look down below, yellow pin number 3 is an output. It's a serial data out. So that needs to hook up to pin 5 of the chip, which is serial data in. And the vice versa for the green cable, which is pin number 4 on the cable, and that's an input. So that's going to be the output of the chip to the input of the cable. So if you have them switched, you're going to get an error, or there's going to be no data found or something like that. We'll see a couple of error messages in a couple of slides. But brown is then chip select to make sure that you're selecting chip. So what does this look like when we are attached to the board? So if you remember correctly, this particular chip was on the back side of the board. So we're hooked up to the back side. Here's our SOIC clip, and this clip can actually clip directly onto your memory chip. It's a little fragile, so when you have it attached, you have to sort of hold it in place. Sometimes it doesn't create a very good connection. So if your memory chip is still attached to the board, it's going to be very fragile. And then you attach the leads from the C232H to the top of the clip. And what we used is the SPI flash that was developed in-house. So basically you run SPI flash -R, you give it a file, and then how many bytes you want to read, and -V is just for verification. It reads it twice and makes sure the data is correct. So what kind of error messages are you going to come across when something goes wrong? And if you remember, there's a couple of things that you're going to find. Device not found. So if you see device is not found, a USB connector is probably not plugged in, or the cable is not attached to the chip correctly. Reading all zeros, that's definitely very, you're definitely going to come across that when the adapter isn't attached. Do you remember when I was telling you that the connector is very fragile and it kind of moves around on top of the chip? Yeah, you might have to, you know, go get a lab partner or a coworker and have them hold down that adapter to your chip to make sure it's making good contact. If not, you're going to be getting this, you know, reading all zeros. If the chip is blank, 9 times out of 10, you probably have the data, the serial data in and the serial data out switched, where you have it data in to data in and not the vice versa. And you have like data out to data out. Do you remember when I was talking about the yellow and green leads? You need to have them switched. That's probably why you would see something like chip is blank. The other type of output you might get from SPI flash is reads are not identical. And that is where it does a read the first time through, and the second time through it's doing a verification, and it finds that the two reads are not identical. So it's probably getting it on the first try, or maybe you hit the adapter or something happened, and the next time it read, it didn't, it's not matching up. So you need to either figure out a way to, you know, hold it there for a number of seconds so that you can read all the data that you need, or it could be something else. The other thing that can happen is Another thing that could happen is you don't have enough power. So the board, when you're reading stuff off of an embedded system, or you're reading stuff from memory, the board is not going to be powered. So you're actually gaining power from the VCC of the cable from your USB interface, and there shouldn't be power to the board at all when you're doing this type of work. But if you look here, there is actually an LED on when I have this attached to the board. And it's like, why is this LED on? Well, because sometimes, depending on how the board is implemented, the power that you're supplying to the chip actually goes out, and it powers some of the other boards. So the chip isn't getting a whole lot of power. It's not getting enough power to power on. So that also can cause the problem and the issue where you're reading all zeros. And when you come across something like that, a workaround that is to be able to add an additional power source that is not coming from the C232 cable, but there's this power source, or a power adapter that we have that's made by USB Reg. And what you can do, it's just a USB power cable where you plug it into the USB, and it can actually supply you 3.3 volts or 5 volts. And then what you do is you take that power, attach it to the VCC of the replace it with the red cable. You take the red cable off, and you take the 3.3 from this USB Reg and attach it to the chip. And then you take the ground from the USB Reg and attach it to some ground header on your board. So it has, it's relative. So you can figure out, it has a reference essentially. And so we try that again. If we're lucky, we get a win. We get, reads are identical and verification is successful, and we can read the entire chip. So that's awesome if it works that way. There are times, and this is also from another board, where you can't do it. And in this particular case, we actually attached the additional power source to the router, and it still did not. We tried many ways. We made sure that our adapter was attached correctly. We moved it around. And in this particular example, it was a 16-pin SOIC. It was the WinBond on one of the routers. We had a straight attachment. We attached the clip directly to the chip, and we didn't get nothing. We kept getting red all zeros, and then we had added the USB Reg power supply. That didn't help at all. Again, we were still reading nothing. So in this case, what you have to do is just remove the chip from the board itself. What 9 times out of 10 is because the power you're supplying to the board is now, it's feeding off into the other board. It's feeding into the other components on the board. Well, it's draining into the other components on the board, and and there's not enough power to supply, or there's not enough power that's going to power the chip. So at the end of the day, what we did is we removed it, and we attached it directly to the SOIC clip, and this was pretty easy. You just put it through and clip it on and try it again. So we tried it one more time. This is for the WinBond, and we were able to extract some data. And what you do after you get the data out of SPI Flash, it dumps it to a binary file. Binary file. And then you can feed that binary file into BinWalk and have it extract. If you use the -E option, it'll extract what it can, and it knows, and it can parse the firmware headers, and it can identify sections that are possibly compressed and decompressor for you. And underneath, it's actually calling Sasquatch. Sasquatch is calling Squash FS underneath, unsquash FS underneath, and then you get this nice output. So if you look around inside, you'll see that we have a Squash FS root. So if you actually go underneath that and take a look, you can see a complete file system. So what happens if you get a binary you're able to read data out of the chip, and you have a binary, data blob. And you put that into binwalk and you say, extract for me, and you get no results. What could possibly be the issue is that the data in there is encrypted. And when it's encrypted, there is almost no way that you can figure out what's inside that. You can break the encryption if you want, but it's highly unlikely. And what you have to do at that point is you have to extract from the interface. Because the reason why you want to extract from the interface is that at some point in time in the boot sequence, at some point, the system or the bootloader is going to read the data out of that non-volatile space where it's been encrypted. It has to unencrypt it and then store it into RAM, and then inside RAM is where it can, it'll be able to execute the data in like plain text essentially. And so since it's in the RAM component is memory mapped. So either using JTAG or the UART interface, you should be able to extract the memory section. So you can copy the contents out of the memory mapped area. If you're doing it over UART, you'll have a command prompt, and then there's going to be an OS running. It's going to be the interface. So it's all up to you how you want to do it. But as far as what we discussed here, in conclusion, it's highly recommended for you to remove the memory component so that you don't have the additional headache of trying to determine whether or not your board is taking all the power you're supplying to the chip. And it's kind of hard to, if it's too hard to like try to leave the chip on the board, sometimes people don't want to remove it, but it's highly recommended just to remove it. It's much easier, it's quicker, it's faster, and just get some really good rework guy to put the chip back on for you, and voila, you're done. The other thing too is like SPI flash only does SPI flash. So if you want to read some of the other bigger chips or things that are not SPI related, and it'd be faster if you just get a reader that supports the chip. But then if you're reading various types of different chips, you may have to have multiple readers. But if you have something like Advin or something like that, it might be able to read multiple manufacturers. These techniques can also be applied to parallel flash, but we didn't discuss that here. It's something we want to go over in the future. But and there's also many more techniques we can cover about extracting memory, and then teaching you the pros and cons of it, and also highlighting additional gotchas when you're trying to extract data from a memory component. So with that, that's the end of our talk today. So if you have any questions, comments, concerns, please email us, get with us, talk to us. The email you can contact us at would be tns@tacnetsol.com, tacnetsol.com. And again, my name's Heather Eastman. Thanks for listening, and thanks for coming. Hope to see you guys in 2 weeks.